The plan for today is to talk about evaluation. So how to, instead of talking about how to build the new types of generative models, we're going to discuss how to actually evaluate how good they are. And it's kind of like a challenging topic where there's not really a consensus on what's the right way to do it, but we'll try to sort of like cover at least some of the ways that are out there. Nothing is perfect at this point, but we'll cover some of it. So just as a brief recap, we've talked a lot about modeling. We talked about different types of probabilistic models that you can use. You can work directly with the probability density or the probability mass function, in which case, we've seen autoregressive models, normalizing flow models, latent variable models like the variational autoencoder. We've seen energy-based models. We've talked about probabilistic models or kind of like generative models where instead of representing a probability density function, you represent directly the sampling procedure. So this is kind of like generative adversarial networks would be one example. And then we've talked about score-based models where instead of representing the density, you represent the score, which is just like the gradient essentially. And that's yet another model family that you can use to model your data. And we talked about a number of different training objectives that you can use to fit a model to data. We've talked about KL divergence, which is the same as minimizing KL divergence is the same as maximizing likelihood, which is a very natural kind of objective to use whenever the likelihood is accessible directly. So if you're modeling directly the probability density function, probability mass function, this is a very reasonable kind of objective to use. And so autoregressive models, flow models, the elbow in variational autoencoders is also kind of like an approximation to the maximum likelihood objective. And to some extent, contrastive divergence is also an approximation to, or it's exact to the extent that you can get perfect samples from the model. We've seen F divergences and two sample tests, which are very natural in the context of generative adversarial networks. If you're the only thing you have access to are samples from the distributions, then this is a reasonable way of training a generative model. And then we've seen Fisher divergence, which is essentially the same as score matching, which makes a lot of sense whenever you have access to scores or whenever you're working with energy-based models, because it allows you to bypass the normalizing constant. And we've seen noise contrastive estimation, which works for energy-based models. And the question is, at this point, there is a lot of different pieces, a lot of different ingredients that you can use. There's many different kinds of model families that you can pick from. There's different kinds of training objectives. And a natural question is, how do you pick which one you should use for a particular data set? And eventually, this boils down to the question of which model is better. Like, should you train an autoregressive model on your data? Should you train a flow model? Should you train a GAN? And in order to answer that question, you need to be able to say, model A is better than model B, essentially. And that requires you to be able to evaluate basically the quality of a generative model. And that's really, really important because you can, allows you to make comparisons and pick a model that is most suitable for your problem. And it's a kind of like, if we think of it from a researcher perspective, it's kind of like a super important ingredient. We always want to make progress. We want to build better models. We want to get better and better. But in order to do that, we need to be able to measure how good a model is, right? And so we live in a world where it's pretty easy to just people make their models open source. You can clone a GitHub repo. You can improve. You can make a change to a model or to a training objective. You get something new out. It's very important to be able to quantify, is your proposed solution better than something that existed before. And again, that requires you to be able to evaluate different kinds of generative models. And unlike the case of discriminative models, typical machine learning models, evaluating generative models is unfortunately pretty hard. In the case of a typical machine learning model that you would use for a discriminative task, say you're training a classifier to label data, so map inputs to labels, so a pretty kind of like low dimensional, simple kind of output space. That's a setting that is pretty well understood, how to measure progress. Somebody comes up with a new architecture for, let's say, computer vision tasks. You can train the models, and you can check, what kind of losses they achieve. You can use it on, you're gonna define some kind of loss that quantifies what is it that you care about. Is it top 1 accuracy, top 5 accuracy, or whatever decision problem you intend to use the predictions that you get from the model in. You can specify a loss function, and then you can try to, given 2 models, you can evaluate the losses that they achieve on held out unseen data, and that gives you a pretty good handle on the performance of the model. That tells you essentially, if you were to test time, when you deploy the model, you were to fit in data that kind of looks like the one that you've been training on, this looks like the one that you have in the test set, then that's the performance that you would expect. And so, that allows you to compare different models and decide which one is better. And unfortunately, things are not so easy for a generative model. It's not clear what is the task. Essentially, that's the main challenge. What is it that we care about? Like, why are you training a generative model? And there is many different options, and all of them are more or less valid. Perhaps you're training a generative model because you care about density estimation. You care about evaluating probabilities of, say, images or sentences. Maybe you care about compression. Maybe you care about generating samples. At the end of the day, you're training a diffusion model over images, and what you care about is being able to generate pretty outputs that are aesthetically pleasing. Or maybe you're really just trying to do representation learning, and so or unsupervised learning at the end of the day. Like, you have access to a lot of unlabeled data, maybe large collections of images or text that you've scraped from the internet. You'd like your model to learn something about the structure of this data, and you'd like to be able to get representations out of the models that then you can use to improve performance on downstream tasks. Instead of working directly on pixels, maybe you can work on representations obtained by a generative model, and then you can get better performance. You can reduce the amount of labeled data that you need to train a model. Or maybe you're thinking about many different tasks that you need to be able to use your model for. Perhaps you're trying to train a single good model over images that then you can use to do compressed sensing, semi-supervised learning, image translation. Or if you're thinking about language models, again, you're sort of trying to find a single model that has been trained on a lot of text, a lot of collected from the internet, and what you really care about is being able to leverage all the knowledge that has been encoded in this big language model, an LLM, and then what you really care about is being able to maybe prompt the model to solve tasks using a small number of sort of instructions or examples. So lots of different things you could do, and these different things will lead, and for each one of them, or for some of them at least, there is many different metrics that you could use to, even if you pick one of these tasks, it's not entirely obvious how you measure performance on each one of them. The simplest one is probably density estimation. If you really care about density estimation, if you really care about being able to accurately quantify probabilities using a generative model, then likelihood is a pretty good metric for that. So what you can do is you can basically split your data into train, validation, and test. You can fit your model using a training set. Maybe you pick hyperparameters on the validation set, and then you can kind of evaluate the performance on the test set, where the performance is just the average log likelihood that the model assigns to on test data, which is a pretty good approximation to the kind of average log likelihood that you would expect the model to assign to samples drawn from this data distribution. And essentially, this is the same thing as compression. We've seen that maximizing likelihood is the same as minimizing KL divergence, which is the same thing as trying to compress data, essentially. So, at the end of the day, what we're saying is that if you use that as a metric, you are comparing models based on how well they compress the data. And to see that, turns out that there is a way to take a probabilistic model and map it to a compression scheme, where what you would do is you would encode a data point X to some string that can be decoded back in a unique way, and the length of the string basically depends on the probability of the data point. So if you have data points that are very likely, they're very frequent, then you want to assign short kind of codes. And if they are very infrequent, then you can afford to assign very long codes. You're not going to see them very often. And that's a way to compress data using a code. And sort of like it goes back to the intuition that we had before. If you think about the Morse code, it's based on this principle, right? So if you have vowels like E and A, they are common, so you want to assign a short code. And then if you have letters that are less frequent, then you want to assign a long code to that. And if you train a generative model based on maximum likelihood, you're basically trying to do as well as you can at compression. And if you compare models based on likelihood, you're comparing how well they compress data, which might or might not be what you care about. And to see that, it's pretty clear that if the length of the code that you assign to a data point X basically is proportional to, it is very close to the log of 1 over P, then you can see that the average code length that you get is going to be this quantity, which is roughly, if you get rid of the fact that the lengths have to be integers, if you approximate it, it's roughly equal to the negative log likelihood. And so if you try to maximize the likelihood, you're minimizing the average length of the code that you get, so you maximize the compression that you can achieve. And in practice, if you use this kind of Shannon or Huffman codes that you might have seen before, it's actually expensive and it's not tractable to actually build one of these codes, but there are ways to get practical compression schemes. And so to the extent that you can get a good likelihood, there is an actual computational efficient way of constructing compression schemes that will perform well as long as you get good likelihoods on the data. There's something called arithmetic coding, for example, that you can actually use. So if you're able to train a deep generative model that gets you good likelihoods, then you can potentially compress your data very well. And this is actually, if you've read papers on language models, the GPTs, and those kind of things, that's essentially the same metric that they use when they compare language models. They call it perplexity in that setting, but it's essentially like a scaled version of the log likelihood. Now, the question is, why compression? Right? Is that a reasonable thing to do? Is that what we really care about? It's reasonable in the sense that as we've discussed, if you want to achieve good compression rates, then you need to basically be able to identify patterns in the data. The only way you can achieve good compression is by identifying kind of like redundancy, identifying patterns, identifying structure in the data. So it's a good learning objective, and we know that if you can get the KL divergence to 0, then it means that you've perfectly matched the data distribution. And kind of this makes sense, like if you're trying to train a generative model to capture knowledge about the world, this it's a reasonable objective. We're training the model to compress the data, and by doing so, we're learning something about how the world works, essentially, because that's the only way to achieve compression schemes, right? And so the intuition could be something like this. Even if you think about physical laws, like Newton's law or something like that, you can think of it as one way of compressing data. If you know there is some kind of relationship between variables you care about, like F equals MA, then knowing that sort of relationship allows you to compress the data. You don't have to store Let's say if you have a sequence of accelerations and forces, you don't have to store both of them. You can store just the accelerations and you can recover the forces through the equation, for example. So any kind of pattern or structure in the data like this allows you to achieve better compression rates. And so by training a model to compress, you might be able to discover some interesting structure in the data, including maybe knowledge about physical laws and things like that. And that's kind of like there's actually something called the Hatter Prize. It's actually like there's a $500,000 for developing a good compression scheme for Wikipedia. And the quote from the prize website is, being able to compress is closely related to intelligence. While intelligence is a slippery concept, file sizes are hard numbers. Wikipedia is an extensive snapshot of human knowledge. If you can compress Wikipedia better than the predecessors, your decompressor is likely going to be smarter, basically. And the whole idea behind this prize is to basically encourage the development of intelligent compressors as a path towards achieving AGI. So the hypothesis here is that if you can really compress Wikipedia very well, then you must achieve a very high level of intelligence. And indeed, you can actually compare how well humans do at this. How good are humans at compressing text, right? There's actually an experiment that Shannon did many years ago, and he was very interested in this kind of topic on compression, and he invented the whole field of information theory. And he actually did experiments checking, how good humans have a lot of knowledge, a lot of context. If you see a string of text, you're probably going to be pretty good at predicting what comes next. And so he actually did an experiment with getting human subjects involved and trying to see how good are people basically at predicting the next character in English text. And what he found is that they achieve a compression rate of about 1.2, 1.3 bits per character. So there are 27 characters or something like that. So there's a lot of uncertainty. Like if you didn't know anything about it, you would need maybe 4 or 5 bits to encode a character. But people are able to do it with only 1 or 2. So there's not too much uncertainty. When you predict the next character in English text, people are pretty good. There's kind of like only, if you think about 1 bit of information, it encodes 2 possibilities. And so that's the typical uncertainty that people have when they predict the next character in text. So kind of like 1 bit would correspond to, okay, there's 2 possibilities and I'm uncertain about them, about which one it is. And you might ask, how well do large language models, neural networks? They actually do better than humans already, and you can get something like people tried on Wikipedia on that Hatter Prize kind of data set, and they were able to get something like 0.94 bits per character. So even better than humans. And again, this is a reasonable objective, a reasonable way of comparing models. That's what people use for training large language models. They train them at maximum likelihood. Makes sense to compare them based on perplexity to some extent, or try to forecast how good the perplexity is going to be if you were to increase data or you were to increase compute, scaling laws, kind of things. But there are issues with compression, and the main issue is that it's probably not a task we actually care about, or not entirely reflective of what we care about. And the issue is that basically not all bits of information are created equal. And so if you think about compression, a bit that is encoding a life or death kind of situation is worth exactly the same as something maybe less important, like is it going to rain or not tomorrow? And so compressing one or compressing the other gives you the same, is the same from the perspective of chaos divergence or maximum likelihood, but obviously it doesn't reflect the way we're going to use the information in downstream tasks. And so there are some serious limitations of what you can say by just comparing models in terms of compression. Think about image data sets, same thing. Like there is certain pieces of information that are much less important to us. Like you could think about a slight change in color for a particular pixel. It doesn't matter too much, while there's information about what is the, what's the label of the image that is much more important. But from this perspective, it is all the same. Basically, it doesn't matter. So that's a main limitation of density estimation or compression. And yeah, we'll talk about this more later. The other thing to keep in mind is that compression or likelihood is a reasonable metric for models which have tractable likelihood, but there is a bunch of models that don't even have it. So if you're working with VAEs or GANs or EBMs, it's not even obvious how you would compare models in terms of likelihood or compression. For VAEs, at least you can compare them based on elbow values, which we know is kind of like a lower bound on likelihood, so it's a lower bound on how well they would compress data. But if you have GANs, for example, how would you compare, let's say, the likelihood that you achieve with a GAN to the one that you achieved with an autoregressive model or a flow model? Like you can't even compare them because there is no way to get likelihoods out of a generative adversarial network.
But I remember when we are kind of learning the GAN part, you mentioned kind of one big motivations about it is it's a lot likely to break.
Yeah.
Right. So let's just try to understand here so does evaluation matrix really depend on looking at the downstream task or?
So it depends what you care about. Yeah, it's a great question. I mean, do you really care about compression? Maybe not. But if you wanted to compare the compression capabilities of a GAN to something else, you would not even be able to do that. And we'll see that, yeah, maybe that's not what you care about. Maybe you care about sample quality, and we'll see that there are other sort of like evaluation metrics that maybe make more sense, where you can say, okay, is a GAN better than an autoregressive model trained on the same data set? But if you cared about density estimation, then you need to at least be able to evaluate likelihoods, and it's not something you can directly do with a GAN. And so, in general, it's a pretty tricky problem to figure out if you have a generative adversarial network and you have, let's say, an image and you want to know what is the probability that the model generated this particular image. It's pretty difficult to do. Even if you can generate a lot of samples from the GAN, it's actually pretty tricky to figure out what is the underlying probability density function. And typically you have to use approximations. And one that is pretty common is called a kernel density estimation that allows you to basically get an approximation of what is the underlying probability density function given only samples from the model. So it would look something like this. Suppose that you have a generative model for which you are not able to evaluate likelihoods directly, but you're able to sample from it. Then you can draw a bunch of samples. Here I'm showing 6 of them. And just for simplicity, let's say that the samples are just scalars. So you generate 6 of them, and the first one is minus 2.1, minus 1.3, and so forth. And these are sort of like representative of what is the underlying distribution that generated this data. And the question is, what can we say about probabilities of other data points? So given that you have these 6 samples from the model, what is the probability, let's say, that we should assign to the point of minus 0.5? And one answer could be, well, the model never generated 0.5, or 0.5 is not among the 6 samples that we have access to. And so we could say, since it doesn't belong to this set of samples, maybe we should set the probability to 0, which is probably not a great answer because we only have 6 samples. It could be just due to chance we didn't see that particular data point in our set of samples. So a better way of doing things is to do some kind of binning, build some kind of histogram over the possible values that these samples can take. For example, you can build a histogram, let's say, where we have bins with 2 here, and then you basically count how frequently the data points land in the different bins, and then you sort of like make sure that the object that you get is properly normalized, so that the area under the curve is actually 1. And so because we had a bunch of, we have two data points landing between -2 and 2, then we have a little bit higher, we assign a little bit higher probability to that region, and then you can kind of see the shape of this histogram is related to where we're seeing the samples that we have access to in this set. And then you can evaluate probabilities of new data points by basically checking where does, in which bin does this test data point land. -0.5 lands in this bin where there's 2 data points, and so we assign probability density 1/6. And then if you take, let's say, -0.99, 1.99, I guess that's also in this bin where there's 2 data points, and so it should also be 1/6. And then the moment you step over to the next bin on the left, then the probability goes down to 1/12 or something like that. So just basic histogram as a way of constructing an approximation of the probability density function based on samples. It's a reasonable thing, but you can kind of see that these transitions are probably not very natural. Perhaps there's something better we can do, and indeed a better solution is to basically smooth this kind of hard thresholds that we had because we were using bins. And so the way a kernel density estimator works is that when we evaluate the probability of a test data point X, we basically check how similar this data point is to all the to all these samples that we have in our set. And we do that using this function K, a kernel function. And then we evaluate this probability by basically looking at all the n samples that we have access to, evaluating the kernel on the difference between the data point that we're testing the density on and the samples that we have access to, and then where the distance is scaled by this parameter sigma, which is called the bandwidth of the kernel. And to make things concrete, you can think of the kernel as being just a Gaussian function that has that sort of like functional form. And so the similarity between 2 data points kind of like decays exponentially based on that equation. And if you do that, then you get a smoother kind of like interpolation. Before we had these kind of bins that were sort of like not very natural. Now what we're doing, if you're doing a kernel density estimator using a Gaussian kernel, is we're basically putting little Gaussians centered around each data point that we have in this set of samples, and then we're summing up basically all these Gaussians, and we get an estimate of the density that is now much more smooth. Right, and so essentially the probability is high if you're close to many data points, kind of like before, but now it's being close is smooth. Like it's not only about whether you are in the bin or not. Now there is some small effect even if you're very far away. Although the effect of a data point decays according to that whatever function you choose for the kernel. Yeah.
Are there some heuristics for how you choose like the variance specifically for your kernel function? Like,
yeah, that's gonna come up next. That's a great question. And it seems like, okay, you choose the kernel. The kernel is basically telling you should be a non-negative function that is normalized. So it integrates to 1, so that when you take this kind of the sum of n kernels, the total area is going to be n, and then you divide by n, and you get an object that is normalized, so you get a valid probability density. And then I guess it has to be symmetric, because it's sort of like intuitively kind of like a notion of similarity between a pair of data points. And so the function value is going to be high when the difference is close to 0. And the bandwidth controls how smooth, basically, that interpolation looks like. And so what you see here on the left are different kinds of kernel functions you could choose. You could choose Gaussian, you could choose more like a square kind of kernel. that kind of like determines how what you think is the right way of comparing how similar two data points are. So if you choose a Gaussian, you have that sort of functional form. If you choose some kind of like square kernel that looks like that, then it's more back to the histogram kind of thing where 2 points are similar if their distance is relatively small. After you're above this threshold, then the distance becomes extremely high. The bandwidth controls the smoothness. And so you can imagine that ideally you'd like to pick a bandwidth such that you get the distribution, like the black one, the black curve here, that is as close as possible to the true curve that generated the data, which is shown in gray there. But you can kind of see that if you were to choose a value of sigma that is too small, then you're going to get something like the red curve, which is very jaggy again. And so it's kind of like under smooth. And if you were to choose a very high value of sigma, then everything is kind of like similar to each other. Then you're going to get a very smooth kind of interpolation, and you get something like the green curve, which again is not a good approximation of the density that actually generated the data. So back to the question, how do you choose sigma? What you could try to do is you can try to tune it by trying to do cross-validation, where you leave out some of your samples and then you try to see which kind of sigma fits the samples that you've left out as best as possible. And so, yeah, that's at least in principle, it's a way that would allow you to compute to get an estimate for the underlying density given only samples. Unfortunately, it's actually extremely unreliable the moment you go in high dimensions. Just because of curse of dimensionality, basically you would need an extremely large number of samples to cover the whole space and all the possible things that can happen. And so the more dimensions you have, the more samples you need. And in practice, it's not going to work very well if you're working on something like images. So there are limitations for what you can do. Now, what if you have latent variable models? If you have a latent variable model, again, but you would like to somehow get the likelihood, in theory, you can get it by sort of like integrate out over the latent variable z. We know that that's sort of like the expression that you would need if you want to evaluate the likelihood of a data point x. You can in principle get it by looking at all the possible values of the latent variables and then checking the kind of conditional probability of generating that data point x given the different z's that you're integrating over. As we know, this can have very high variance, sort of like if the distribution of the prior is very different from the posterior, which basically means that, again, you're going to need a lot of samples to basically get a reasonable estimate of that likelihood. And yeah, there are ways to basically make the estimate more accurate. There is something called an yield importance sampling, which is a procedure to basically do importance sampling by constructing a sequence of distributions to draw these z variables that is kind of like interpolating between the bad, sort of like naive choice of just sampling from the prior p of z and the optimal thing that you would like to do, which is to sample from the posterior. And we're not going to go into the details. Let me actually skip some of this stuff. But if you have, in your project, you're working with latent variable models, you have a VAE, and somehow you need to compute likelihoods, you might want to look into these kind of things because they might help you get more accurate sort of estimates of the likelihoods that you get from your variational autoencoder. Cool. Now, what about sample quality, right? In a lot of these situations, we maybe don't care about likelihoods, we don't care about compression. We have two generative models, maybe, and we can produce samples from them, and we would like to know which one is producing better samples. Let's say if you're working on images, maybe you have two groups of samples, and you'd like to know which one is better. And how to do that is not very obvious. It's actually pretty tricky to say, is this generative model that produced these samples better than the generative model that produced these samples? Not obvious how you do that. Probably the best way to go about it would be to involve humans. Ask some annotators to essentially compare the samples and check which ones are better. And of course, that's not going to be scalable. Maybe it's not something you can use during training. But if we have the budget for it and we have the time to go through a human evaluation, that's usually sort of like the gold standard. There is actually very interesting work in the HCI community where people have explored what are principled ways of getting feedback from humans and try to figure out, and get them to compare the quality of different types of samples or different kinds of generative models. This paper is actually from Stanford, kind of like looking at perceptual evaluation of generative models. And which is based in psychology, cognitive science kind of literature, what they suggest is that what you should do is you should take samples from your model, you have real data, and then you can kind of check how much time people need to accurately decide whether or not the samples that they are seeing are fake or real. So if you can only look at a sample for a very small amount of time, you might not be able to perceive the difference from what is real and what is not. Maybe the hands are not rendered correctly, but if you don't have enough time to actually stare at the pictures long enough, you might not be able to see it. And so what they suggested is that we need to look at this time to get a sense of, the longer it takes for people to distinguish real from fake, the better the samples are. And the other metric that they propose is more traditional, and it would basically be the percentage of samples that deceive people when you're giving them an infinite amount of time to actually check, are these real or not? And so, you can look at the website if you're interested. And this is sort of like what it would do, what it would work like if you want to determine how much time it takes for people to figure out whether or not samples are real. What you do is you might start with maybe a fairly large number of maybe 500 milliseconds you give them to decide whether or not the image is real. Maybe they always get it right because they have a lot of time to figure out what kind of mistakes are made by the generative model. Then you start decreasing the time you give them until you get maybe around 300 milliseconds where people start kind of like not being able to distinguish real from fake. And at that point, that would be sort of like the hype time score for this particular generative model. And then, as I mentioned, sort of like the longer it takes people to figure that out, the better the samples are. And here you can see some of the examples, and then you can also rank different samples based on how long it would take for human evaluators to basically distinguish different types of samples. Now, the problem with human evaluations are great, and maybe you can use them for your project. The problem with human evaluation is that they tend to be expensive. You actually have to pay people to go through the process of comparing samples, deciding which ones look better. They're hard to reproduce, and they are strange. You need to be very careful on how you set up these human evaluations. The layout that you use to ask them questions affects the answers that you get. The way you phrase the questions affect the answers that you get. So it's actually very tricky to rely entirely on human evaluations, and they tend to be pretty hard to sort of like reproduce. And so the other thing you might not be able to get if you just do this is you might not be able to actually evaluate generalization. Like again, if you imagine a generative model that is only just memorizing the training set, it would give you very good samples just by definition, and you might not be able to, even you use humans, you might not be able to actually figure out that indeed the model is actually just memorizing the training set and it's not actually able to generalize in any meaningful way. And so it would be nice if there was some kind of automatic evaluation metric to actually figure out the quality of the samples. And some that are very popular, that are often used in the literature and you might need to implement or use also for your projects are Inception scores, FID scores, and KID scores, which actually I think came up at some point in the last lecture, and there were questions of what they actually are. So now we're going to see how they are actually computed and what they actually mean. So Inception scores is something you can use when you're working on labeled data sets. So if somehow you're in a setting where the images have associated labels, then what you can do is you can try to essentially predict the labels on synthetic samples. And you can check what kind of distributions over the labels you get on synthetic samples versus real samples. So if you have access to a classifier that can essentially tell you what's the label for an image, X, then what you can try to do is you can try to quantify how good a generative model is by looking at the behavior of the classifier on the samples that it produces. So there's two things that the Inception score looks at. The first thing it looks at is something called sharpness. And essentially, you can imagine two sets of samples, one that looks like this and one that looks like this. And if you were to, this is a labeled data set, every sample has a label, which is just the number. This is MNIST, so it's kind of like a toy example, but every digit, every image you produce can be mapped to a number that it represents. And you can kind of see that somehow the true samples are probably relatively easy to classify, while synthetic samples that are a little bit blurred, they're not very clear, they're going to be harder essentially to classify if you have a good classifier. So the intuition behind sharpness is to basically look at how confident the classifier is in making predictions on the synthetic samples, on the generated samples. So the formula looks like this, and it's essentially something related to the entropy of the classifier when evaluated on samples. So you generate samples from the model, and then you look at all the possible predictions that the classifier produces over the x's that are synthetic. Then this quantity here is basically related to the entropy of the classifier. And so when the classifier predictive distribution has low entropy, so kind of like the classifier is putting all the probability mass on a single y, it's very confident in the prediction that it makes, then the sharpness value is going to be high. And the other thing we want to check is something called diversity. And the idea is that if you're working with a labeled data set, you'd like the model to essentially produce images of all the classes that are represented in the training set. So if you have, let's say, a GAN that generates samples that look like this would indicate something like mode collapse, where it's only producing once. And we would like to somehow say, okay, these are not good samples because there is not enough diversity. And the way to quantify it is to basically look at the marginal distribution over the labels that you get from the classifier when you evaluate it on the samples. And you basically try to make sure that this marginal distribution has high entropy, meaning that all the classes that are possible are actually predicted by the classifier over the synthetic samples, essentially. So it is not just producing once, the model. That's the formula. Again, it's basically looking at the entropy of the marginal distribution. Then the way you get the Inception score is you multiply together these two numbers. And so high Inception score is good because it means that you have high diversity, then you have high sharpness.
So how do you evaluate in-class diversity? Because with something like this, it seems like you could just take a bunch of rollouts and then just average the number of times it's predicted 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Just make sure that the distributions are all about the same. But seems a little bit harder to say. Within the class, I have several different ones drawn.
Yeah. So it doesn't do that. So that's the problem. Yeah. So it's not perfect, and yeah, that's one example of a failure mode. Like if somehow, yeah, it does represent all the digits, but only one kind of digit, you would have potentially a high inception score, even though you're sort of like dropping modes within the clusters, kind of like corresponding to different labels. So not perfect for sure, but widely used nevertheless. And so higher inception score corresponds to better quality. Why is it called inception score? Well, if you don't have a classifier, so if you're not sort of like in the MNIST or TOY sort of like situations, what you can do is you train a classifier, train an image net, like the inception net, typically that people use for this, and then you compute these metrics with respect to that.
Can you go over this diversity? How is it exactly assessing diversity again?
So it's basically checking, so this C of Y, if you look at it, is basically the marginal distribution over the predicted labels when you fit in synthetic samples. So if you were to only produce ones, then this CY would be like a one hot kind of vector, and then the entropy would be very low. And so you would be unhappy basically. And so you want high entropy, meaning that ideally it should be uniform. This CY should be uniform over the different Ys that are possible. So then that means that all the classes are represented in equal numbers, essentially. Yeah.
So doesn't that mean that if you want to increase diversity, you would decrease sharpness?
Yeah, so they're competing, yeah, and you would like to have a high value of both. And cool. Okay, so that was one. It's often used, but as we discussed, not perfect, far from perfect. One issue is that you're kind of like only looking at samples from the synthetic samples, but you're not really ever comparing them to real data. If you think about these formulas, you're just looking at synthetic samples, you pass them through the classifier, then you look at statistics of what comes out from the classifier, which seems suboptimal because you're never even comparing synthetic samples to real samples. So there's something called an FID score, which tries to essentially compare the similarity of the features extracted by a large pre-trained model on synthetic samples versus real samples. So what you do is this: you generate a bunch of samples from your generative model, and you have a bunch of real data from, let's say, the test set. And then you feed each sample through some kind of pre-trained neural network, like an Inception net, for example. That's why, again, it's called FID score. And then you get features for each data point. There's going to be a distribution over these features because every data point is going to have a different corresponding feature vector. And what you can try to do is you can feed a Gaussian to each to the features that you get from the synthetic samples and the features that you get in the real samples. And you're going to get two different Gaussians, meaning that the Gaussians will have different means and different variances. And the closer these two Gaussians are, the closer the higher the quality of the samples, essentially. Because if the samples from the synthetic model are very different from the real ones, then you might expect that the features that are extracted by a pre-trained model are going to be different, and therefore these two Gaussians might be different, maybe have different means, or they have different standard deviations, different variances. Then you get a scalar out of this by taking the Wasserstein-2 distance between these two Gaussians, which you can compute in closed form, and it's essentially looking at the difference between the means of the Gaussians and some quantity that basically quantifies how different the variances that you got by fitting a Gaussian to the real data and the fake data are with respect to each other.
So what's the intuition for using multivariate Gaussians? Like, why not any other statistic?
Yeah, you could use other things. The reason they use multivariate Gaussians is that this Wasserstein-2 distance can be computed in closed form. But yeah, not particularly principled. Yeah.
Won't this depend on the samples that are being drawn? So, like the generated, considering an imaging model, so the generated samples could refer to maybe some other subject area of images, and the trained ones could be some others. So, are we really comparing apples to apples? Like,
Well, if the model is doing a good job at fitting the data distribution, then you would expect the statistics extracted by a pre-trained network would also be similar. So if, for example, this pre-trained network is extracting statistics, high-level features like what's in the image, where the objects are located, and things like that, which you might expect these networks to do because they perform pretty well when you fine-tune them on a variety of different tasks, then in some sense you're hoping that looking at the statistics will tell you something about how similar the samples are in terms of do they capture a similar distribution.
So 2 questions related to the feature thing. First one was that why we fitting multivariate Gaussians to the features? What about checking the mean and variance of the generated and the test samples directly? And the second one was can you elaborate on what for example, variational autoencoders, we try to compute like a feature representation, right? So is that what you're referring to when you say feature representation? Anything?
So for the second question, the features are the ones that are extracted by a pre-trained model, which could be anything. In the FID case, it's Inception net. That's why it's called Inception distance. And so that's a pre-trained model, typically on some large-scale image data set, where you have a lot of different classes. In order to perform well, classification probably has to extract reasonable features. Comparing in the feature space kind of makes sense. The other question was, why not just compare the means of the samples themselves? That would be a very simple kind of feature, right? Where you're just looking at the individual pixels. You could, but it may be not exactly what we care about. It's more interesting to compare these higher level features that are extracted by a model.
When you're using FID, do people ever add auxiliary losses to the training part itself, like I don't know, UGG or something, to make this metric be better downstream, or is it separated?
Yeah, you could train on FID, then you can no longer use it as an evaluation metric. So it's not the moment you start training on something, it stops to become a good, So, but you could, yeah, to the extent that it's not too expensive to compute, which I think it might be, but you could try at the very least. And then, in this case, so lower FID is better. And the other thing you can do is to do something called the kernel inception distance. And the idea is to basically do a 2-sample test, kind of like the same thing we've used for training models, but instead of doing it at the level of the samples themselves, we're going to again do it at the level of the features extracted by a pre-trained model. And so the MMD is another kind of 2-sample test where you have samples from 2 distributions, P and Q. And what you do is you compare the difference in different moments, kind of like what's suggested by Dev right now, looking at the mean, the variance, and so forth. And more specifically, the way you do it is back to the kernel idea. You use a kernel to measure similarity between data points. And what you do is you do this. If you have distribution P and Q, you check what is the average similarity between 2 samples, 2 real samples, let's say. What's the average similarity between 2 fake samples, and then you compare that to the average similarity between a real and a fake sample. And if P again is equal to Q, then you can see that this thing evaluates to 0 because the difference between real and fake samples is the same as the difference between 2 real samples or 2 fake samples. And the idea is that we're now allowed to use a kernel to basically compare how similar 2 samples are. And so we don't necessarily have to compare samples in terms of their raw pixel values, but what we can do is we can again sort of do MMD in the feature space of a classifier. And so what you would do is you would use a kernel to compare the features or two samples, two real samples, two fake samples, and a real and a fake sample, basically. And it's similar to FID. The key difference is that KID is a little bit more principled, but it's more expensive because you kind of like, if you have n samples, then it has kind of like a quadratic cost as opposed to a linear one because you have to make all pairwise comparisons between the two groups of samples. But similar flavor to FID.
So how does FMB compare the two distributions moments?
It's because it's not obvious from this perspective, but you could also think of it as basically the kernel. You could basically map the samples in the reproducing kernel Hilbert space of the kernel. So it's kind of like if the kernel is comparing data points based on some features, then this is basically the same thing as kind of like embedding the real data points and the fake data points in the feature space of the kernel, and then comparing those two objects. But the nice thing is that the kernels could be looking at an infinite number of features. So it's kind of like the kernel trick, where you're allowed to compare data points using an infinite number of features without ever having to compute them. Okay, so that was the three main kind of like metrics that are used for evaluating sample quality. There is many more that you might need to consider, especially if you're thinking about text-to-image models. Then there's many things you have to worry about. So if the generative model is supposed to take a caption and generate an image, then you do care about image quality, but you do care about other things. For example, you care about whether or not the images that you generate are consistent with the caption that was provided by the user. But then you might care about other things. You might care about the kind of biases that are shown by the model. You might care about whether or not it's producing toxic content that you might need to filter. How good it is about reasoning, about if the caption talks about different objects and their spatial relationship, how good is the model at understanding the sort of spatial relationship and spatial reasoning kind of problems. So it's actually something pretty new that also I was involved in, came out of Stanford. So we put together this benchmark called HAIM, Holistic Evaluation of Text-to-Image Models, where we've considered all the different metrics that we could think of, and we've considered different kind of evaluation scenarios. And so you can see some examples here, trying to look at quality, where maybe we use the usual FID and Inception and KID that we just talked about, but then we also look at other things, how robust the models are, if you change words in the captions and the alignment between the image that you generate and the caption, various kinds of aesthetic scores, various kind of originality scores. So a lot of different metrics, and we actually try to do, what I think to date is the most comprehensive evaluation of existing text-to-image models. We took a lot of existing models, and then we try to compare them with respect to all these different metrics. And you can go, if you're interested, and see the results and see which model produces the highest quality images as measured by all these different metrics, both real, both human and automated, or other things. If you care about the biases that these models have, we have a bunch of metrics to measure that. So that might be a useful kind of resource, again, as you develop your projects. Now, another things you might want to do with the model is to get features. We've talked about this idea of kind of like doing unsupervised learning. You have a lot of unlabeled data. You might be able to get good features from the model. How do you evaluate whether you have good features or not? Which you know already, what's the task you are thinking about? You're trying to get features because then at the end of the day you care about classifying. You have a classification problem in mind. Then you can always sort of like measure the performance on the downstream task. So in that case, it's not too hard. It's a lot more tricky to, if you don't have a task in mind and you're just trying to say, okay, is this model producing better features than this other model? Then it's a lot more tricky to be able to see something definitive there. And there is different aspects that you might want to consider if you are in the unsupervised kind of setting where there is no task, there is no labels, so no objective way of basically comparing different sort of representations that you might get. You might care about how good the model is at clustering. Maybe you care about compression. Maybe you care about disentanglement. So maybe you care about this idea that we briefly talked about, that if you have a latent variable model, you would like the latent variables to have some kind of like meaning, and maybe you might want to be able to control different factors of variation by changing the variables individually. So that's what's kind of like referred as disentanglement, where the different variables have kind of like separate meanings and they control different aspects of the data generating process. So if you care about clustering, ideally you would like to be able to group together data points that have somehow the similar meaning, or that they are similar in some way. And this is all very cyclical, but that's the problem with unsupervised learning. And one thing you can do is you can take your VAE or your model that gives you latent representations. You can map points to this feature space, and then you can apply some kind of like clustering algorithm like k-means to group them together. And so here's an example of the kind of thing: you train two generative models on MNIST, and then you map the data points to a two-dimensional latent space. And here the colors represented the different classes. I don't even remember exactly what is B and what is D, but these are two different models, and they produce two different kind of embeddings of the data. And which one is better? Is B better? Is D better? It's unclear, right? They both seem to be doing something reasonable, where kind of like data points belonging to the same class end up being grouped together in this latent space. It's not obvious which one you would prefer. And so, for labeled data sets, again, there is many quantitative metrics. So if you do have labels that you use to, so you use unlabeled data to come up with the clusters, and then you use labels to kind of like evaluate the quality of the clusters. Then there is a bunch of metrics, things like the completeness scores, homogeneity score, V measures. I'm going to go through them quickly, but sort of like there is a bunch of measures that you can use. If you have a labeled data set, you pretend you don't have the labels, you get representations, you check, you do clustering, and then you can use the labels to see how good the clusters that you get are. And intuitively, what you want to do is you would like to be able to group together points that belong to the same class. And so maybe you care about making sure that all the points that belong to the same class land in the same cluster, or maybe you care about homogeneity within the clusters. So you would like to make sure that all the points that land in the same cluster have the same label, or maybe some combination of these two scores. So there's different metrics that you can use. And again, if your project kind of like involves something like this, you can look into this into more detail. Another thing you might want to do is to check how well basically the latent representations preserve information about the original data points. So to what extent basically you can reconstruct data given the latent representations, which is kind of like the task you care about if you're trying to do lossy compression. So you have data, it might make sense to map it to a latent representation, especially if that latent representation is kind of lower dimensional. And in this case, maybe you care about being able to reconstruct the original data point as accurately as possible. So here you see some examples of kind of like different representations, and you have the original images on the top, and then what you see here is what you get if you map them to the latent space, and then you try to reconstruct the image from the latent representation. And so you'd like the reconstructions to be as close as possible to the original data, while basically reducing the size of the latent space as much as possible. So here, for example, they are looking at different kinds of representations, where maybe if you compress using JPEG, you would get something like a 17x compression in your in your images with a small loss in accuracy or quality, while there are these other representations that you get from training a generative model, where maybe you can get something like a 90x compression, meaning that the latent vectors that you get by mapping data to the latent space are much smaller than the original data points, and still you're able to do very well at reconstructing the original data points as measured by kind of reconstruction metrics like mean squared error or PSNR or SSIM.
Weren't we already trying to do this back when we were discussing VAEs and other latent variable models?
Yeah, so VAEs have a reconstruction loss embedded in them. So it would make sense that they do reasonably well at that. But if you had a different model, maybe you're looking at the representation that you get from a GAN, and you want to know, are those better than the ones I have from my VAE? It depends on what you want to do with those representations. Do you care about clustering? Do you care about reconstruction quality? So this is one aspect that you might care about if you're trying to compare two different types of representations that you get in generative models. Now, the other thing that you might care about the latent space is disentanglement. The idea that we would like these latent representations, the latent variables, to kind of capture independent and interpretable attributes of the observed data. Something like if you have a generative model of faces, maybe if you change one of the latent variables, you change the skin color of the image you produce, or maybe there is another latent variable that kind of like controls the age of the people you generate through this generative model and so forth. And so, for example, maybe there is a latent variable Z1 that is controlling the size of the objects you produce. So if you don't change Z1, then the size of the object never changes. And as soon as you change this Z1, then you change the sizes of the objects you produce. Or yeah, that sort of like would be the ideal outcome. Kind of like PCA, sort of, but in a nonlinear way. You find important aspects, latent factors of variation in the data, and then you're able to control them separately, essentially. And again, there's many metrics that people have come up with. For example, the accuracy of a linear classifier that tries to predict a fixed factor of variation, and a bunch of others that I'm not going to go over. But there are some libraries that would allow you to compute these metrics. So if you're doing a project around disentanglement, this might be a good resource to look into. And the kind of like unfortunate aspect here is that it's provably impossible to learn a generative model that is disentangled if you only have unlabeled data. So if you never get to see the true kind of latent factors of variation, there is no labels associated with these factors that you're trying to discover from data. It's actually provably impossible to do this. So there's been some empirical success, but it's not well understood why these methods work, and there is some theoretical results showing that it's actually not possible. So I guess there are some limitations there. Cool. Now the other thing that, of course, is very popular these days is this idea that if you are working with a language model, perhaps you don't care about going through this process of, well, let's take the data, let's map it to a latent space, and then let's try to somehow use these representations to improve performance in some kind of downstream task. If you have a generative model of language, then you might be able to directly use the model to solve tasks that involve language by basically by specifying the tasks in natural language. So there are kind of like two different ways of using the generative model. You could try to train the generative model in an unsupervised way, and then try to leverage the knowledge that it discovered by mapping data points in this latent space, and then training classifiers the usual way on these latent representations. Or if you're working on with a language model, then there is this idea of kind of like pre-training the model using a lot of unlabeled data, and then trying to adapt it, for example, through prompts, to actually get it to solve a variety of different tasks. So even though these models have been trained by maximum likelihood, which we know is just compression, we know that they are if they do well at compression, it means they've learned something about the structure of the data, they've memorized a lot of interesting things, and then the hope is that we can leverage that knowledge in different kinds of downstream tasks. So for example, let's say that you're doing sentiment analysis, where you're basically given, let's say, a review, or maybe of a movie, and the goal is to predict whether the sentiment of that review is positive or negative. It's a classic kind of like NLP task. How would you use a language model to solve this problem? And the idea is that because we're working with natural language, what you could do is you could try to, so we have our interface is a model that takes a sentence and predicts the next word, right? Let's say it's an autoregressive model. It takes a piece of language and then it predicts the next word. Then what you can do is you can craft this sentence here such that this prediction, that is the only thing the model can do, predict the next word given the previous text, is actually solving the task for you. And so what you can do is you can construct a sentence like classify the sentiment of the movies below as either positive or negative. Then you give it an example of a movie review, which is positive maybe, this has got to be one of the best episodes, blah, 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 with a positive sentiment, and then you give it another example, maybe with negative sentiment, and then you have this review that you'd like to classify, and then you fit in the text of the review, and then you have sentiment, and then blank. And then you use the model to predict the next word, and you use the model to predict what should you replace blank with, which is exactly consistent with the API of the model, which is predict the next word given some context. Then if the model predicts positive, then you're going to classify this as a positive example. And if the model outputs negative there, then they're going to classify it as a negative example. And so this is an example of prompting. And of course, there's many smarter ways of doing it. There's a whole prompt engineering kind of job where people supposedly are good at extracting knowledge from the models by crafting smart prompts. But that's sort of like the basic idea, getting the knowledge from these generative models by kind of like crafting prompts such that encode the kind of task that you want to solve without actually going through representations. Of course, it's also possible to just fine-tune the model, which is closer to the idea of getting representations. You could also just take the model and then fine-tune it to solve the tasks you care about. So presumably, the pre-trained model is already mapping the inputs, like a sentence here, to some representation that is good for predicting the next word. And so you might be able to fine-tune the model to do something interesting. That's also quite successful. I think prompting is perhaps nicer because it doesn't involve any training. That is somewhat special for language models. And it tends to work pretty well, especially if the language model is a very powerful one. And again, what kind of tasks are you going to consider? That's still very much an open problem in terms of like which generative model of language is better, right? There's many of them out there. How can you say whether model A is better than model B? And you can compute perplexity, which is the same as likelihood, but does not quite reflect what we care about. Maybe what we care about is all these kind of scenarios that we might want to be able to ask questions to the language model, or we might want to ask it to do movie reviews for us, or whatever it is that we care about, or do math, or solve riddles for us, or do question answering. And so again, this is a space where it's not clear what is the right task to consider. And so one way to go about it is to kind of like consider a lot of different tasks, a lot of different scenarios, a lot of different metrics, because maybe you care about accuracy, but maybe you care about other things. And you can try to see how these different models that exist out there perform on all these different tasks. So you can consider different scenarios, you can consider different adaptation strategies, let's say different prompting strategies. You can have different metrics, for example, accuracy or whatever it is, when you use the model to solve the task that way, and then you can compare many of the existing models that are out there with respect to all these metrics. And that allows you to maybe say in a more precise way, this model is better than this other model with respect to these metrics on these kind of scenarios. And so again, there is different efforts out there. There is one from Stanford, Helm, that looked at a lot of different metrics, a lot of different scenarios, a lot of different, which is very thorough. There is one that was led by Google, where it was more like a collaborative effort where they ask a lot of people around the world to come up with tasks, and then they are all part of this big benchmark where there is over 200 tasks that you can ask your language model to solve, and you can see sort of like the performance that you get across these different tasks.
How could we adapt this idea of prompting to tasks, the inputs where there is no natural way of sequentializing the data?
So you're thinking of sort of like images or something like that? Yeah, I think it's a good question that somehow the prompting idea has not quite been applied so heavily to say if you have a good generative model of images, how can you use it to solve tasks through prompts? And it's not as natural because the output is an image, and instead of like it's easy to think of the output of to map, say, labels to text or even bounding boxes to text. And so if the API of your model has text as an output, it's relatively easy to use it to solve a variety of tasks. I think it's a bit less natural if you think of if the API has images as an output. But it might be possible. I think it's an interesting kind of like area that people are still exploring. And I don't think there's anything particularly good there, but yeah.
So GPT-4V actually answers questions about answers zero shot, like there's no idea of prompting there. Do you have an idea how it works?
Well, they don't say it, yeah, but I mean, it has probably been the underlying mechanics. It's just predicting the next word, right? And then it has been probably done something with instruction fine tuning, so it has been actually pre-trained on a lot of unsupervised text, just predicting the next word. That's just compression. It wouldn't probably do very well if you start asking questions in a zero-shot way. And so what you have to do is you have to sort of like fine-tune it on a slightly different kind of data set that is emphasizing more the sort of tasks that we might expect the model to be asked at the inference time. And again, there is a little bit of a question of what is the right way of, what kind of task, what is the right distribution? Like, do we care about movie reviews or do we care about question answering? And how do we weight those tools? It's not clear that seems to help, but we don't yet have a good handle in terms of like evaluating or seeing what works and what doesn't. It's very coarse at the moment. No, go ahead.
I think it's becoming clearer when it comes to text, maybe, but maybe I need to look at the image model, like all that stuff, instruction fine tuning and stuff, sure, and like alpaca here reproduce something like that, and then since then other models. But what about image stuff?
We're doing actually like using similar things in just right now. We're basically working on applying. I mean, no, we are not the only ones, but people are trying to do basically. You train a model on a lot of images on the internet, but then maybe you really have there's some kind of like underlying preference that we would like the model to generate, images with higher aesthetic value, or maybe we would like the model to be non-toxic, or we would like the model to be more fair, less biased. And how do you adapt the model to that kind of downstream use? And so what you can do is you can collect preference data, and maybe you can have a caption, you produce 2 images, and you ask a user which one do you prefer. You get preference data on what we like and what we don't like, and then you can fine-tune the diffusion model to be more consistent with this kind of preference data. And so that's possible too. Yeah.
So what are the pros and cons for solving the test by fine-tuning the large language model or prompt engineering?
Yeah, so prompting is great because you don't have to actually, you don't have to have access to any compute, you don't even need to know how to program, right? The only thing you need to do is you need to be able to specify in natural language what you want the model to do. And so it can be completely done sort of like in an in a black box way without even having to know what the model is doing, what the weights are. Fine-tuning requires you to actually train the model for a little bit at least on some new data or some new task or something new. So the bar is a lot higher in terms of like the cost and the expertise that is required for that. Depends. Typically, yeah, it's a better way of doing things, I think, although people have gotten pretty good at prompting, so yeah, I think it depends on the task. Cool. Yeah, so well, I guess we're out of time, so it's perfect timing, but basically I think the takeaway, very high level message is that it's still a pretty open kind of area how to evaluate generative models. There is still a lot more that we don't know. Like we have some coarse ways of comparing and models, and we have a sense of, okay, we're making progress over the years, but there's a lot more work to be done in this space in terms of like coming up with better metrics. And even if you have all these large scale benchmarks where you have a lot of tasks, a lot of metrics, it's still not obvious how you weight them and what is the right distribution of tasks you might expect to use the model on. And so, yeah, lots of work to be done in this space. But hopefully this was helpful. I know many of you are starting to get into the weeds of the project. And so I'm sure you have a lot of questions on how to evaluate models. And so hopefully you got a sense of what's out there. Fortunately, we don't have any definitive answer yet, but at least that gives you some ideas of the kind of things you can use for the project.